Hello, good morning or afternoon, everyone. Thanks for attending our webinar today. I'm just going to start sharing my screens here. Okay, awesome. So again, thanks for attending the webinar today. Our webinar today is titled Understanding Elastomer Fatigue, Crack Growth Testing for Engineering Solutions. So today we'll be talking about one of our third-party lines, the Metravib DMA, or dynamic mechanical analyzers. So we'll be kind of focusing on this equipment and how you can use it to analyze crack growth and fatigue performance. And we'll just go through a couple case studies later on. But before we get to the dessert, we got to eat our veggies first. So I'm just going to go over some theory real quick and kind of go over the importance of crack growth. So first of all, what is cracks and why do we care about them? So rubber materials are designed for applications where they're going to be repeatedly loaded. And this repeated loading can change the material properties, cause mechanical breakdown. And if cracks are formed, can cause incremental growth of cracks as well. The issue with these cracks is that they can propagate during operating conditions. So conditions that we assume are safe for our material to operate at will propagate during operating conditions. And the issue too is that these will propagate until failure, which can be a small issue, or in the case of a tire, for example, can be sidewall blowout, which is a major issue for tire companies, especially when you factor in heat buildup as well. So this can be a really, the title does kind of carry some significance. Small cracks can equal big problems, especially if you don't factor for them. So how do we predict something that's going to happen 3 years, 5 years down the road? Is this magic or science? So luckily for all of us, this is science and not just prediction. Looking at a magic 8-ball, for example. This will mostly be done through what I'm going to label as a black box. This can come in the form of a computational model, finite element modeling, empirical equations that are well established, where we'll essentially input material properties, measured material properties of the material, and use that with the model to predict long-term performance at the R&D stage. We're going to be focusing on crack propagation here for this webinar, but I think it is important to note whether you have a very accurate model or very accurate measurement, you need both. You can't have one without the other. The best model in the world won't work well without accurate measurements, and your best measurements, if you don't have an accurate model that predicts the performance, they won't be worth anything either. So both of these go hand in hand in predicting long-term performance. So just to kind of break down on a macro scale what's happening here, when a crack forms, the cyclic loading or periodic loading will cause the crack to open and close, and this will incrementally cause the crack to propagate or grow. And what's actually happening here is that the polymer chains are incrementally breaking inside the sample here, and that's what's causing the crack to propagate, is the small incremental breakage of these chains. Which from my description so far makes it seem like rubber probably isn't the best material for resisting cracks, but it's actually due to the viscoelastic nature of the rubber that makes rubber suitable for this application. The viscoelastic nature of rubber will allow the energy applied to the crack to be dissipated in other areas of the material, preventing a lot of the energy that's being applied to the material to be dissipated where the crack's not located, greatly reducing the rate of crack growth here. So this will usually happen in front of the crack, reducing the crack growth rate. This is due to the hysteresis behavior of the material, which I'll touch on in a later slide here. So now we kind of understand how crack growth operates. How do we measure this, or how do we quantify this so we can compare it? The most common way to do this is plotting your crack growth rate versus your tearing energy, which will give you a curve that looks something like this. On your y-axis, the lower your crack growth, on your y-axis here, the lower it is on the y-axis suggests a lower crack growth rate, or that your material resists that crack growth a little bit better. And the higher it gets on your y-axis suggests or signifies that your material is cracking faster. And then on your x-axis here, we have your tearing energy, which is a function of our strain. So low strains are related to the low tearing energy, which is on the left side of our curve or our plot. And then high strains are on the right side. So we'll generally see this curve, or this shape of curve here. However, the shape and the exact positioning and values associated with this curve are all specific material properties. So this won't look the same for every material, and different conditions as well will change the shape of this curve. And this curve gives us quite a bunch of information on how a material will crack, or if it will even crack. So just starting from left to right, we have zone 1. This is below the threshold tear energy, or tear strength, sorry, or the intrinsic strength there. Basically, if you're operating below this tear strength, your material will ideally never tear, or the crack will never propagate, I should say. You can design materials to operate in these conditions, but as the material is being used, as it oxidizes, chemical breakdown, sometimes the intrinsic tear strength that we measure in the lab will not hold in long-term conditions. And then we have zone 2 and 3, which is where our crack will propagate. The benefit of this zone, or these zones, is that our crack propagation follows, or can be predicted, especially in zone 3, where it follows a power law. It is a little scary to think that we're operating where cracks propagate, but we do this already with aircraft, where we understand the loading conditions that material is going to be subjected to, and we can use that to predict the life cycle of the material. And finally, zone 4, this is where we get above the critical tear strength, and the crack will quickly propagate to an unstable length. You never really want to operate in this zone. This is bad news bears. So yeah, stay away from zone 4, I guess is the takeaway from that. So this can be measured pretty simply with a crack growth experiment. So the crack growth rate is just the change in length over a known number of cycles. And that's just measured by repeatedly loading the sample. We can do this through a sinusoidal wave, Haversine, triangle, pulse, custom waves. You can do it however you like, and then just measure the change in length over these periods. And we measure the crack growth usually under different conditions. This can be atmospheric conditions, force, but the most common one is the tearing energy. And just to kind of touch on the tearing energy, which is the x-axis for that plot I showed earlier, it's often denoted as G or T. It's the amount of energy required to propagate the crack. For a shear sample, which the Metravib DMA uses, and following ISO 27727, it comes in a shear sample, and the tearing energy for that type of sample can be calculated from the following equation, where H is the height of the uncut sample, and W is the strain energy density. And this is the elastic energy released during the crack growth. And like I mentioned earlier in the previous slide there, not all that energy makes it to the crack tip, and that's due to that hysteresis effect of the material. So the plot on the right here shows the hysteresis curve. And for the strain energy density, we're going to take the area underneath this hysteresis loop. We're not going to include the area inside this loop due to the fact that this energy is being dissipated due to the rubber viscoelastic properties, which is a benefit because it's reducing the amount of energy that is being applied to the crack. And just kind of give us a quick example of what one of these charts will look like. So here's crack growth rate versus tearing energy plot provided by LRCCP in France, where we have two different materials, EPDM and SBR rubber. And we can see here at low tearing energies, both of these materials show similar crack growth rates. But as we increase our tearing energy, or our strain, the amount of force this material is seeing, we see that the two begin to differentiate. This is on the logarithmic scale as well. So this is in the order of decades, the difference between these two at high tearing energies, which kind of shows the importance of measuring crack growth rate. If we understand how the material will crack under different conditions, and we understand our application, we can optimize our material selection. For this example, for example, where SBR might be a better use case for a high tear strength application, like a belt that could be subjected to like a high tear energy, while the EPDM might be more suitable for low tearing energy conditions. And just to kind of touch on ISO 27727, the testing standard that I've referenced here a couple times, it uses shear sample geometries, which are shown in the picture below. It's a thin film, and essentially this material or this sample geometry will isolate the crack growth to one direction to allow us to easily measure it and isolate the effect. This tearing energy on the x-axis there is characterized through a strain sweep of an uncut sample, which is done before the test. And then the sample is cut to initiate the crack at a known location. And then essentially what we'll do is repeatedly strain the sample at a specific tearing energy and tension, and the cracks are tracked with a high resolution camera. And the crack growth rate, again, is defined as the change in length of the crack over the number of known cycles. I did just want to touch on a couple of the Metravib features with the way that they do crack growth testing. So there is a lot of automation in this. The Metravib DMA can measure up to 4 cracks simultaneously. The camera will autonomously track all these cracks, so you don't have to worry about doing the measurement manually. The machine will do it all for you on a slider. And then you can design the experiment to do one specific tearing energy or do a sweep where the machine will do multiple tearing energy stages for you. So it will do the measurement for you at a specific tearing energy, and once the crack is stabilized and you have a crack growth rate associated with that tearing energy, it will move on to the next one. For anyone who's done crack growth testing, this test can take quite a long time, so your machine can run by itself for a couple days and you can get all your crack growth measurements you need without any user intervention. You also get the precise control with Metravib's proprietary shaker technology that gives you direct displacement control. It can allow you to apply different waveforms, kind of like I talked about in the previous slide. We have sinusoidal, Haversine, custom, pulse. Sinusoidal waves are great, but we don't really see those in nature too much. We're usually seeing some random waveform pulses. So understanding how the material cracks under those loading conditions can be important. I have a case study that kind of looks into that a little bit further. And finally, you can control the tearing energy via force, strain, displacement. So you get a lot of control with the proprietary air-bearing shaker technology. And finally, too, just to kind of go back to our black box example here, I'm focusing on crack growth propagation today, but with the crack growth module with the Metravib DMA, you also get the capability to have a DMA and crack growth unit all in one system. So you can measure the creep, the heat buildup, mechanical degradation due to fatigue, the viscoelastic properties. So it gives you a lot of weapons in your arsenal to use as inputs for your material model. And next, I just want to go through some applications for crack growth testing here. So the first one is from LRCCP. It's labeled Fatigue Crack Growth Behavior of Filled SBR Compounds, Influences of Several Parameters and of the Loading Scenario. I've attached the abstract here. I won't go through it all, but essentially I'll just summarize it some. So the group did fatigue crack growth tests on SBR and silicone rubber using Metravib DMA, and some of the effects they were considering included the influence of temperature and the cyclic waveform on these materials. So the two tests I'm going to focus on here are how they considered the influence of temperature. They considered -10, 23, and 100 100 seems really high in terms of what we see in the environment, but due to the heat buildup that a tire will see during operation, 100 degrees Celsius could be happening in your tire due to the poor thermal conductivity of the material, as well as the heat generation due to the internal friction of the rubber material as it's deforming. And then finally, to look into the influence of a mechanical overload. This picture is a little bit of an exaggeration, but I don't know. I think it's pretty funny. But anyway, so what they did was they provided a crack growth measurement, and then they did a large overload on the material, and then measured the crack growth measurement again to replicate the effect of potholes. I'll go into that a little bit more during that portion of the case study to kind of just describe what an overload is. So the first effect they looked into was temperature. So on the plot here, we can see the crack growth rates for, I believe this was the SBR, at -10, 23, and 100 degrees Celsius. So we can clearly see that for the same material, as the temperature increases, the resistance to crack growth rate will decrease, meaning that a material that's hotter will crack faster. So this can be the big issue with tires in terms of sidewall blowout. If they heat up, they get to an unexpected hot temperature, the resistance to cracks is greatly reduced, causing the sidewall to blow out, which is a serious issue for tires. But we can also see too, for lower temperatures, that the crack growth resistance is greatly reduced too. So just to kind of show you the science that's going into your tires there, considering multiple different environments and temperature conditions. And what the group did too, which I like, is they included a couple pictures, and what they noticed at 100 degrees Celsius was the cracks became very unstable, began to form multiple cracks and rapidly propagate, just to kind of emphasize of how unstable and unpredictable these cracks were, where they're kind of starting to not really be true to that power law effect. The cracks started to just become very unstable during the experiment. The next is the overload effect. So essentially what's done here is the group did a crack growth measurement, overloaded the sample by applying 80 newtons of load, and then measured the crack growth rate again. For those that are not familiar, an overload is just a larger load applied to the sample in between the measurements, and an overload will cause the reduction of your crack to propagate, which is a little bit, in my opinion, as I come from a mechanical engineering standpoint, I wasn't expecting that. This is something kind of new to me, which I thought was kind of interesting. But we can see here from the results, the blue curve is the crack growth measurement before the overload. We can see that it has a higher crack growth rate because it's higher on the y-axis. The x-axis for this plot is the number of cycles, so we can see how the crack growth rate changes with cycles. And then they applied the overload of 80 newtons, and then the green curve here is the measurement of that crack growth rate after that overload, and we can see it's greatly reduced and begins to stabilize at 50 newton meters per cycle, where before it was up near 150, 200 newton meters per cycle. The group also again shared the pictures here, and we can see that both the cracks deflected after the overload. And this overload, there's a couple mechanisms at work here. I'm sure there's members in the audience here that know a lot more than I do, but essentially there's a couple mechanisms that could be at play here. It could be blunting of the crack tip, crack closure, or this large compressive or overload stress is causing a large amount of residual stress in the material, which is reducing the crack growth rate. The final case study I want to go through is just looking into the impact of different loading cycles. So this paper titled Waveform Impact on Thermo-Mechanical Fatigue Crack Growth of a Non-Crystallizing Rubber, Experimental Observation and Numerical Simulation, looks into how different loading conditions can change your crack growth rate, as well as your heating, internal heating. So what the group decided to do was they compared a sine waveform to a pulse waveform, which is more in line with real service conditions of a tire. A tire, one point on the tire is only excited for a very small amount of time, and then it has no loading condition until it makes contact with the road again, and then that loading condition starts. So it's not really a sine wave that the tire is seeing. It's more of a pulse signal. And what the group found was the shorter pulse excitation time generated more heat buildup and had a faster crack growth rate. And they related this to the higher hysteresis energy. So we'll kind of look into that here. So what I thought was particularly interesting with this was the group used an infrared camera to monitor the crack growth rate as well as the heat generation during the experiment. Rubber materials are great, but they have poor thermal conductivity most of the time, which when they're deformed, the internal friction of the material will cause heat to generate, and they really have no ability to dissipate that heat. And what the group did was they considered different waveforms. They considered the ideal sine. They considered a pulse waveform that lasted a quarter of a second, as well as one that lasted 150 milliseconds, so a shorter pulse wave. They also constructed a model to predict the thermo-mechanical behavior and to relate it to the model. I won't touch too much on that, but if modeling is of interest for you, I definitely recommend checking out this paper to see that half of it. So they considered, as I mentioned, they considered 3 different waveforms, and they tracked the heat buildup through an infrared camera here. And we can see on the right, the heat buildup for these 3 signals here. So the short pulse wave is shown on the top, and we can see that the internal temperature of that sample during testing was reaching up to 59.7 degrees Celsius, while the sine wave was only reaching temperatures of 51.9 degrees Celsius. Now that's 8 degrees Celsius in the difference. That might not seem like a lot, but when we consider what's happening with the crack growth rate here for these materials, we can see that the black curve, which is our small pulse wave, has a much higher crack growth rate compared to our sinusoidal wave or loaded sample, which is shown in the blue. So this group related it to the thermo-mechanical effect of the material, where the heating of the sample was reducing the crack growth rate, as well as the hysteresis effect of the material. So if we look at the curve here, plotting the stress versus strain of this material with the Metravib DMA, we can see that the area of the curve for the small pulse waveform is larger than the sinusoidal waveform, which means that there's more hysteresis energy being dissipated in the material with the shorter pulse signal. More energy dissipation means that there's more heat being generated in the material, reducing the resistance to crack growth rate. I also have the values here on the right, just to kind of show a numerical comparison. So the sine wave had the short pulse there had what is that? That's about 40% increase compared to the sinusoidal waveform. If we compare the two, so a much larger hysteresis energy generating heat. And although this doesn't seem like a big issue for one cycle, if we consider a tire that's going on the highway, it's going to have hundreds of thousands of cycles going, and this is where that heat buildup can be a big issue. So in conclusion, crack growth can be characterized with the Metravib's crack growth module. Crack growth rates are affected by temperature. This can be external temperatures from weather conditions, as well as the internal temperatures generated through heat buildup. Crack tips are also affected by loading conditions. This can be including a one-time overload, as well as an oscillatory loading, such as pulse or sine waves. And that's the end of the presentation there. So if you guys found this interesting, we also have additional resources online at C-Therm.com. It has our previous webinars, tech library, if you ever want to do a paper search. We also have an upcoming event in Novi, Michigan, the Thermal Management Expo. But if you're around and you want to talk crack growth, we'll have representatives there as well who can educate you on the topic. And for other upcoming webinars, we have a webinar with Sarah Ackerman on how to measure the thermal conductivity of metal hydrides. We seem to be getting a lot of interest in that topic, and particularly excited to see what Sarah does with that webinar. Be sure to follow us on LinkedIn as well for any upcoming events. That includes where we'll be at for shows, special events, webinars, you name it. So we're always putting stuff up on there. And I guess finally the last thing is for questions here.